All right, it's the final exam review. Finally, we're at the final. Lots of finals. It's exciting. This is the last big push, and then we're done. We're done with the semester. We're done with this crazy semester. So crazy. So, anyways, this is it. I have the review and everything posted online. And then this is the last little bit. So we're going to take it all the way back to chapter 1. Just a little side note. The chapter 4 stuff is at the very end of this section, because some instructors teach chapter 4 at the end of the semester, while I chose to teach it after chapter 3. So chapter 4 content is at the very end of this review. So if you're wondering why that's out of order or why we skipped it, that's why. There's like a little bit from there that is covered in like chapter 14.1. And so that's why they do chapter 4 stuff at the very end. Anyways, I did it in the middle of the semester. So I just wanted to give you some insight on that. So we're going all the way back to chapter 1, and we were talking about some definitions. So it says, know definitions and identify examples of qualitative, quantitative, discrete, and continuous variables. So the first one we have here is nation of origin. And the question is that quantitative or qualitative? Well, remember that quantitative is something that is like a number. It defines a quantity of something, like a count. And then a qualitative variable is something that describes a quality or a characteristic of some sort that is not numerical. So when we talk about nation of origin, that's not a number. It's not something that's countable. So this would be qualitative. Qualitative. And so for that reason, it is neither discrete or continuous, because discrete and continuous only applies to quantitative variables, not qualitative. So if it's qualitative, it cannot be discrete or continuous. Number of siblings. Well, that's a count, something you can count. So that would be quantitative. And I guess I should kind of backtrack a little bit when I say countable. So I should say that something that's quantitative, again, is numerical, a quantity of some sort. It doesn't necessarily have to be countable. It could be a measurement of sorts. So that will determine actually if it's discrete or continuous. So when we're talking about the number of siblings, I said that's countable, right? That's something you can count. Is a finite number of siblings that you would have. In that case, this would be discrete. So really, if you're looking at, you kind of look at, is this like only whole numbers, or do decimals make sense here? So if decimals would make sense, then it would be a continuous kind of situation. But here you can't have half of a sibling, or a third of a sibling, or a fourth of a sibling, or something like that. 0.1 of a sibling doesn't make sense. So that's why it's discrete. Generally, anytime you see the words number of in front of something, that means it's going to be discrete. Okay, grams of carbs in a donut. Well, sounds like a number, right? It is, so that one's quantitative. And the question is, do decimals make sense here? Can you have 1.1 grams of carbs in a donut? Can you have 0.2 grams of carbs in a donut? Yes, you can. Decimals make sense here. Yeah, you can have half of a gram. So this one would be continuous. Generally, if it's a measurement of some sort, continuous, then it will be continuous. Outside air temperature. So again, that sounds like a number. So that's quantitative. Oops. So many T's and I's. Well, just only 2 I's, but lots of T's. Okay, so quantitative. And the question is that discrete or continuous? Well, it's a measurement. So that one would be continuous. Okay. Finishing place in a race. This one's a tricky one, right? So when we're talking about a finishing place in a race, we're talking about like first place, second place, third place, right? And you're thinking those are numbers. Not really. those are more like names of like the places that you're in. So first place, if you think that's actually, that's not one. It's not like you could add those numbers together and it would make sense. Like you can't say first place plus second place equals third place or something like that. That wouldn't even make sense, right? So you can't do any kind of operations on these quote unquote numbers when we're talking about finishing place. So finishing places or things like I think on the extra credit I give you, this was like a movie ratings or something like that, like 1 star, 2 star, 3 star. Those are more separating things into different characteristics, right? Different groups. So this one is actually qualitative. Kind of tricky. So of course not discrete or continuous because it's qualitative. Weight of a child, that's a number, so quantitative. And that is weight, so that's continuous. It's a measurement. Okay, year of birth. Okay, well, year of birth, that's a number. That's quantitative. And the question is it discrete or continuous? So, like, can you have, so your year of birth, so like mine's 1986. But would it make sense to have your year of birth as like a decimal, right? Could I have been born in 1986.2? No, that doesn't make any sense at all. So decimals and things don't matter. They don't make sense here. So in this case, this is actually discrete. Okay, so that's chapter 1. Let's see here. Number 2 says, be able to identify a random sample. Determine if the following are random samples. So just knowing what a random sample is. The first one says, put all student names on slips of paper, fold the papers and put them in a hat, then blindly select 5 slips of paper to have 5 students in our sample. Does that sound random? Yes. It's actually a simple random sample because everybody has an equally likely chance of being chosen. So, yeah, that is a random sample. So we would say yes. Random sample. Okay, assign all patients a unique ID number beginning with the number 001 and ending with the number 507. Have a trusted computer program generate 50 random numbers between 1 and 507. And the patients with the selected ID numbers are included in the sample. So when I first read this one, I was like, is it a random sample? Is it not? Is that all patients? Is it not? I was a little, to say the least, I was just a little confused. So when I looked at it again, I consulted a colleague and everything, and we talked about it a little bit. I think we came to the agreement we think it is a random sample, and here's why. So it says assign all patients a unique ID, which means you're talking about all patients, right? So that's your whole population. They're all getting a unique ID number. Starting with 1, ending with 507. And then it says, have a trusted computer program generate 50 random numbers between 1 and 507. So you're creating a sample of 50, and you're choosing out of every single patient, so all 507, 1 to 507. And then you just include the ones that have that selected ID. I mean, really, the big keyword here, I see the word random, 50 random numbers. So to me, that says it's a random sample, right? So I would say, yes, this is a random sample. Okay. Part C, randomly select. Okay, well, right there, I see the word randomly select. And I'm going to go with, yeah, it's random. So random numbers, randomly select. So I think these are all just kind of ways you can see what a random sample looks like. But yeah, I don't even have to read the rest of this. I can say it says randomly select. But randomly select 50 residents from each state, Alabama, Alaska, etc. The 2,500 selected individuals are in the sample. So yeah, I would say that is a random sample. Yes. Random sample. Okay. Number 3. Interpret measures of center and dispersion and determine appropriate uses for each. And then these are, by the way, these are just kind of your topics, I should say. Objectives. Let's see, objectives. Use measures of central tendency to identify possible shapes of distributions. All right, so we got data set E has a mean of 54.2, a standard deviation of 2.3, and a median of 55. And data set F has a mean of 21, standard deviation of 15.2, median of 32. Which data set is the most consistent? Okay, so consistent means that your data is all relatively close together. They're not very spread out, things like that. So when we're looking at which one's the most consistent, well, what tells us the spread of the data is not the mean and not the median. Those are measures of center. But measures of dispersion, or the spread, that's going to be your standard deviation. So the smaller your standard deviation is, the closer your numbers are together. The bigger your standard deviation, the farther apart your numbers are. So when we're looking at these two data sets, I see that E has a standard deviation of 2.3 and F has a standard deviation of 15.2. Well, the smaller spread would be more consistent. So that would be data set E. So data set E, since it has a smaller spread. Okay, next page. Page 2 of 16. Okay, what is the expected shape of the distribution for data set F? So I'm going to go ahead and write down kind of what was on the previous page so that we have that data here. Oh, I shouldn't put equal signs. Okay, so data set E, I'm going to go with, this is a population mean. Population mean is 54.2. Standard deviation is 2.3. And I ran out of room, so, oops, wrong button. Chaos. Okay, and then your median is 55. Okay, and then for set F, the mean is 21.0. The standard deviation is 15.2. And the median here is 32. Okay, so now let's look at this question again. What is the expected shape of the distribution for data set F? Okay, so we're looking at F here. That's this one. And we want to know what is the shape, right? Well, if you remember way back in chapter 2, I think, when we talked about this stuff, we were trying to figure out, what is the mean and the median when you compare them? What does that tell you about the shape? And if the mean and the median are approximately the same, then that means you're looking at a symmetric distribution. If they are relatively different, then this is going to be a skewed distribution, a skewed shape, right? So if I'm looking here at mean and median, 21 and 32, I see that those are pretty different. Those are not the same. So the next thing is I want to know, okay, so my mean here, which is 21, is less than the median, right? So if the mean is less than the median, what that means is that in your graph, the mean, okay, so remember the mean gets pulled in the direction of your extreme values because it is not resistant. It's heavily affected by those extreme values. So wherever you have your extreme values in the tails, that pulls the mean in that direction. So I'm looking at the mean here is 21 and it's smaller than the median. Okay, well, if the mean is smaller than the median, it's being pulled to the left, which means this is a skewed left distribution. So this is skewed left since the mean is less than the median. Okay, for which data set is the mean the best measure of center? Okay, so coming back to the resistance and what what it means to be resistant and things like that. Now, the difference between mean and median. Mean is using all your data points, okay? So it does not suffer any loss of data because you use every single data point. So this is going to be your better measure of center if your graph is symmetric. Okay, if it's not symmetric, then median's actually your better measure of center because it more accurately represents the middle of your data versus the mean. And that's because you have extreme values in those skewed graphs. So as we just talked about in part B, the mean is pulled in the direction of this extreme values. So it's not resistant to those extreme values, whereas median is. So when we talk about which data set is the mean, the best measure of center, well, if it's a symmetric distribution, in other words, the mean and the median are about the same, mean is your better one because it includes every data point instead of just one or two, if it's the median, right? It could be one or two. The mean includes everything. So it's going to be your better measure of center for data set E because I'm looking here and it says that data set E is, you've got mean and median, which are relatively close together. So for data set E, since mean is equal to median, this means that well, let me not write it that way. Let me say data set E, since it is symmetric, hold on. I want to say this one more, differently. Okay, my apologies. Data set E is symmetric. There we go. Is symmetric. Because the mean, well, I'll just write the word mean, is approximately the same as the median. Therefore, the best measure of center for a symmetric graph, so mean is best for symmetric graphs. And I'm just going to go ahead and put a little note here that median is best for skewed graphs. I should say distributions. Okay. So I did leave a little extra space here because I wanted to draw a few pictures just to kind of demonstrate the difference here. So I wanted to show, okay, that one's a little too intense here. There we go. Okay, sorry. All right. Well, those aren't great, but I guess they'll suffice to show that this one here is skewed left. Okay, and the mean is here, the median is here. I know those look kind of the same, but we would say the mean is less than the median. And a box plot that would match this would look something like this. We got the longer tail over here, and oh gosh, I don't remember where I put the, I know for sure the longer tail. I'm trying to remember where I would put the longer or the wider side here. I'll come back to that. But your median is going to be generally off to one of the sides. So I think it's like this. We've got the wider gap here and the longer tail here. Don't quote me on that, so I'm going to delete that for just a minute. But let's see here. This one right here in the middle, this is the mean and the median. So this is symmetric bell-shaped. And this kind of box plot would look something like this. that one would be in the middle. And then this one over here, this is going to be your median. Well, maybe not right in the middle here, but okay, your mean is going to be kind of over that way. So for this one, this is a skewed right graph. So you got the longer tail on the right there, and this is where the mean is greater than the median. Oh, dang it. All right. Mean equals the median. I should have put that above that. That bugs me. Okay. So then this one here would have something that looks like this for a box plot. Longer tail. I think something like that. Gosh, I can't remember. I'll have to look back in my notes. So maybe I'll pause it and take care of that and look at my notes. Okay, sorry, I have to fix this. Mu equals median. Those are about the same, right? Okay, there we go. All right, I'm going to pause. I'm going to look at my notes. Okay, yes, upon further investigation, I was right initially when I put these where I did. Something like that. Okay. So, yes, these are there. So you have the wider space in the box where the longer tail is for those skewed box plots. And by the way, this is chapter 3. I think I mentioned chapter 2. This is chapter 3. So I think chapter 2 was talking about frequencies, relative frequencies, and things like that. Chapter 3 was all about measures of center, and I think we even talked about measures of central tendency, measures of dispersion, mean, median, mode, all that kind of stuff, standard deviation, empirical rule. That's all chapter 3. So yeah, chapter 2 is a different chapter. So this one here is going to be chapter 2, frequency tables and stuff. So construct and analyze frequency distributions, histograms, stem and leaf plots, box plots. So it's kind of both chapter 2 and 3. It says Nielsen/Net Ratings is an internet media and market research firm. One variable they measure is the amount of time an individual spends viewing a specific web page. The following data represent the amount of time in seconds a random sample of 25 surfers spent viewing a web page. So we've got all our data here, and very conveniently it's put in order for us, so we don't have to, sort through all the data. It's I would say it's generally not like that, but you can always, your data is going to be probably in a spreadsheet. I mean, you're not going to have it handwritten. So if you put it in a spreadsheet, you'll sort it. I mean, gosh, you'd have the spreadsheet do everything anyways, but so it is sorted, which is nice. It says construct a frequency table and report the relative frequency for each class. So frequency, and it started off for you, telling you that everything from 0 to 24, there's 11 of those. So if you go up here and you count, and I'm going to color code this a little bit. So 0 to 24 seconds, that's going to be all the way to here. Okay, so let me come over here. There you go. Okay, so that's everything in 0 to 24 seconds. And if I just count them, then it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 11 of them. Okay, so that's 0 to 11 right there. Okay, the next one, we want to count everything that is from 25 to 49 seconds. So we're going to do that. And let's come here. So starting at 26, going up to 49, that's there. Okay, so there's 1, 2, 3, 4, 5, 6, 7 of those. So 7 here. I'll underline it in orange. Actually, I should underline this in orange. There we go. That's better. Better. Okay. Okay, 50 to 74 seconds. So 50 to 74. Looks like we've got these guys up to here. So it looks like there's 4 of them. 75 to 99 seconds. So there's 2 of those. And then 100 to 124. That's this lone number there. So there's one of those. Okay, so our frequency should add up to the total number of people here. And it says a random sample of 25 surfers. So when we calculate, if I add up all my frequencies, they should total 25. And they do, right? So the sum of the frequencies is 25. And so if I'm trying to find the relative frequency for each class, then the relative frequency is like part out of total. So the formula, I guess, relative frequency is equal to the frequency divided by the sum of the frequencies. Okay, so 11 divided by 25. That's your little formula. So I'll go ahead and put the fraction here, 11 out of 25, which equals 0.44. And then we've got 7 out of 25, which should be 0.28. 4 out of 25, 0.16. 2 out of 25, 0.08. And 1 out of 25, which would be 0.04. And if these are exact numbers, now your fractions are exact, but your decimals are not. Well, those are exact, actually, in this case. We didn't have to round anything. Those are exact. So if I add up the total of my relative frequencies, the sum of the relative frequencies should equal 1. Okay? Now, if it doesn't add up to 1, like if it's 1.001 or 0.999, something like that, that's just because of rounding errors, if you rounded. Okay? Now, if you didn't round and it doesn't add up to 1, then that's a problem. You made a mistake somewhere. So make sure it adds up to 1. Okay, so we've constructed this. Now, let me just say, what if I asked you, okay, what if I only gave you the frequency table and I said, tell me the relative frequency of the second class? Okay, well, you'd go, well, which one's the second class? Actually, you'd probably go, okay, I'm guessing the second class is the second one. You'd be right. This is the first class. This is the second class. This is the third, the fourth, the fifth, right? So if I asked you to find the relative frequency of the second class, and you didn't have these over here, you'd go, oh, well, my frequency is 7. The total of my frequencies is 25, so 7 out of 25 would be 0.28. That's how you do that. Just saying. Okay. Next one is still on the same table. It says construct a histogram, stem and leaf plot, and a modified box plot of the data. So there's like 3 things that we're going to be calculating here. It's going to take us a little while. So let me go ahead and get started. We'll start with the histogram. I think I tried to leave enough space to go ahead and go straight down with them. So I'm going to try and do them a little bit small. Histogram. Okay. And when we do our histograms, we're going to use the relative frequency up here. So actually, let me do this on the side. I'm going to go ahead and just write relative frequency. I'm going to abbreviate because I don't have enough space. And then down here, this was the time in seconds. Okay. Now, our time in seconds was divided into classes, right? And when you set up your classes, now you start here at 0, that's 0, right? And the first class was 0 to 24 seconds. So I'm going to go ahead and put here, I'm going to do all my lower class limits, right? So 0 is a lower class limit. The next lower class limit, so the second class started at 25. That's the one we're going to put on here. We're going to start off with all of our lower class limits. So 0, 25, 50, 75, and 100. Okay. Then on the side here, we're going to do our relative frequencies. So our relative frequencies, the highest one was 0.44. So as long as we go to at least 0.45, we're good. Now I don't have that much space here, so I think I'm just going to go up, count up by 0.1, 0.2, 0.3, 0.4, and 0.5 like that. So 0.5, 0.4, 0.3, 0.2, 0.1. Okay. Now, of course, on your final this is going to be given to you. You're not going to have to draw this. You're going to have to be able to read it and interpret it, though. So knowing how to kind of read this and understand what it's saying. Okay, so 0 to 25, that was 0.44. So it's going to be about here. And then we're just going to come straight down on the 25, because that's like the, that's where it's going to butt up against the next one. Okay. And if you want to, you can go ahead and put here 0.44 above. Then, the next one is at 0.28. So just here, but below the 0.3. Okay. 0.28. Then 50 to 74, that was at 0.16, so it was about there. 0.16. 75, oh, you know what? I didn't do the next lower class limit. What would the next lower class limit be? So if we're counting up by 25s every time, this would be at 125, right? Okay, so 75 to 99, that was 0.08, so just a little below the 0.1 there. And then our last one is at 0.04, so it's going to be about there. 0.08, 0.04. There we go. So there's our histogram. And if we wanted to make a statement about the shape of this histogram, I think we would say that this is a skewed right. Oh, hold on. Describe the distribution of the data set and identify any outliers. Let me pause there because that's on the next question. Okay, so let me just draw the histogram and then move on with our next one. Okay, I can't help myself, but I need to shade this. This is just, it needs some color here, okay? Just need that little bit of, I hate when it's like all black and white. It's just hard for me. It like just makes it so blah. Okay. Pen, black. Okay. All right, there's our histogram. Okay, next thing we want to do a stem and leaf plot. And so a stem and leaf plot, let's see, I think I could work maybe across stem and leaf. Okay, so for the stem and leaf plot, the first thing we have to do is come up with our legend, like our key. What is it? What does everything represent? And so usually you start with kind of your very first thing on your list. I'm going to come back to the previous page to show you the list. Okay, so the first number on our list here is going to be a 4, right? So in our legend, the ones place is going to be our leaves, and all of these have tens, right? And the tens place is going to be our stem. So our stems are going to start with 0, because this is a 0, 4, and 0, 5, right? And then the last in the tens place here is this 11. So we're going to go from 0 through 11 in our stems, and then these are going to be all of our leaves, all these numbers over here. So let me come back over here. First, I need to state that 0, 4 represents 4. Okay. And it's not like 0.4, because it could be, depending on what your numbers are, right? We're not dealing with those decimals. So in our case, it's just representing 4. And then our, like I said, our stems. So stems, leaves. Okay, so we said they're going to have to start at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, good, I have plenty of space. Okay, and then my leaves are going to go, okay, now I'm going to tell you, because I already have these written down from the previous table, but remember, I'm just going off of this information. So we used this class's frequency, relative frequency, to draw the histogram. And then now we're using all of this raw data up here to create the stem and leaf plot. So I'm going to look at where my tens place is a 0. Okay, and I've got a 4 and a 5. So my leaves for that one are going to be 4 and 5. Okay. Then over here, for my ones, I'm sorry, when 1 is in the tens place, I've got 10, 11, 12, 12, 14, 15, 19. Okay, so my leaves are going to be 0, 1, 2, 2, 4, 5, 9. Okay, So I try to space them out so that they're like kind of lined up here. So 0, 1, 2, 2, 4, 9. Then for the 20s, I've got 0, 3, 6, 7, 7. You'll notice that these are all in order. They should be. They always will be in order, least to greatest. Number 3. So 30s. In the 30s, I've got 31. In the 40s, I've got 40, 42, and 48. So 0, 2, 8. In the 50s, I got 51 and 51. So if there's two 51s, you put both of them down. Okay. Each one should be represented here. There's 65 and 69. 75, 83, 75, 83. There were no 90s and no 100s, and then we had 111. So then that's just going to be a 1 there. Okay, so this here really represents kind of a histogram. So if you turn your paper, and I don't know if I'm going to actually, if I would be able to even do this. If it would turn, yeah, I can't do it. Oh, wait, maybe if I lock it? Oh, that's not going to change anything. Never mind. You guys can't see me turning my tablet. Okay, well, I'm going to go ahead and just do something here. So this here kind of creates what looks like a histogram, right? If we just put little, that's why I wanted to keep my numbers kind of aligned here. Just so I can have some accurate bars. Okay. So now if we're looking at this, should have done all those in a different color, huh? I was going to like shade here. All right, so if we've got, well, you can still see the numbers, right, if I do that. Okay. All right, so now if you're kind of looking at this, this almost like gives you like the data, right, within your histogram. So it's like a sideways histogram, but all your data points are accounted for and they're all in there. So that kind of gives you a general shape there. If you were to turn it, you know, to the side and look at it standing up, it's going to look a lot like this histogram over here. A little more spread out, but still has the same general shape. And the last thing we need to do here is to do a modified box plot. Okay, so modified box plot. A modified box plot means that if you have outliers, then you're going to denote the outlier on your box and whisker plot. So we need to figure out some stuff. Like we need to know our lower and upper fences so that way we can determine if there's an outlier. So we need to know like the minimum value, the first quartile, the median, third quartile, all that stuff in order to draw a box and whisker plot. So I'm going to show you, actually I don't have this in the calculator. So I'm going to pause and put all the data in the calculator and then I'll show you where you can find your 5-number summary. Okay, so I have the data in the calculator. Let's go ahead and look where we can find our 5-number summary. So if you go to Stat and then go over to Calc, remember 1var stats, which we did like forever ago. We're going to use 1var stats. I put mine in list 1, so we're going to leave frequency list empty and then just hit calculate. And if you scroll down to the bottom, you'll be able to see here, this is your 5-number summary. We've got 4, 13, 27, 51, and then 111. So I'm going to go ahead and write those down on the paper here, but that's how you can find them. So I'm going to put my min is 4, first quartile is 13, Q1. The median is 27. The third quartile is 51, and the maximum is 111. Okay, so we need to figure out what is our interquartile range. So on your formula sheet, I believe it tells you the interquartile range. Let me just take a little look here at my formula sheet. I really should have that on here so I can demonstrate my formula sheet, but I think you guys all have it with you, so you should be able to look at it. But yeah, the relative frequency formula is on here. Okay, interquartile range is Q3 minus Q1. So IQR equals Q3 minus Q1. You're probably wondering, well, why do we need that? Well, I'll tell you, we're going to need that in order to find the lower fence and the upper fence, which will determine if we have any outliers. So we are going to have to check for that. Okay, so Q3 minus Q1. So in this case, 51 minus 13, which equals 38. Okay. Now to find our lower fence and our upper fence, so the lower fence is going to be Q1 minus 1.5 times the interquartile range. Okay, and actually I'm going to go ahead and I'm going to write it. No, I'm going to leave it this way. I like it this way. Okay, so Q1 is 13 minus 1.5 times 38. I guess... No, I'm going to change this. Give me a second. Okay, you might be wondering why I did that. And I'll tell you why. Because a lot of times what people do here when they make a mistake and they do 13 minus 1.5 first. And as long as you remember your order of operations, you remember you have to multiply first. But it makes it a little more obvious that you multiply first if you do it the way that the formula is on the formula sheet. So I'm going to go ahead and write that here the way it is on the formula sheet already. So 1.5 times 38. Okay, so if I calculate my lower fence, I get negative 44. Okay, well, none of my values were less than 4. My minimum right up here, my minimum is 4. So I'm good on the lower fence side. There's nothing below my lower fence. I mean, we're really good there. So my upper fence though, so that's going to be Q3 plus 1.5 times the interquartile range. So Q3 plus 1.5 times 38. Oh, sorry, let me plug in Q3. Duh. Okay, Q3 is 51. Okay, so 51 plus 1.5 times 38 is going to give me 108. Okay, so now if you look at our maximum value, right? You see that? The maximum here is 111. That is above my fence. So I'm going to do a quick demonstration here. Just a little on this. Oh, whoa, what happened? Okay. Okay, so here's your fences. Well, actually, I'll show you when I draw our fences, and I'll show you how we do an outlier. Now, since a 111, okay, so outlier is 111. Since that's an outlier, we need to figure out like just the x value, the next highest x value. Okay, so if you go back to your data, and we see here that the next highest number is 83. 83 is going to be where we stop at our quote-unquote maximum. That's not an outlier. It's the maximum value that's not an outlier. So I'm going to go ahead and put that back here. We're just going to call, we're going to say here, I'm just going to put x equals 83, just kind of as our new maximum, so we know how to graph it. Okay, I'm going to try and do my box and whisker plot. I think I have enough space over here, I guess. Yeah, I have enough space. Okay, so we're going to put 0 here. And I'm going to go up, I'm just going to go up to 125 like I did on my frequency distribution. So let's see here. 25, 50, 75, 100. Well, try that again. 25, 50, 75, 100. Okay, so we'll move the 125 over just a little bit. About there, 125. Okay, there we go. Okay, so, well, dang it. Oh my gosh, guys. Okay, sorry. I need to have the box and whisker plot floating above. Let's do this. 25, 50, 75, 100, 125. There. Okay, now I can do my box and whisker plot above. Okay, so I need to put my lowest value on here. So my lowest value, my minimum was 4, right? So I'm going to just do this. I guess I'll stick with this color. My lowest value is 4, right? Well, here's 25. 4 is going to be pretty close to the 0 here. So we're just going to come up here and we're just going to put a little vertical line, just a small one, to show our minimum value. Okay, the first quartile is 13. So 13 should be right about halfway here, right? So I'm going to do a longer line, connect those. That's my first quartile. Then I'm going to do my median, which is at 27, so just a little bit after the 25 here. Okay, and then my third quartile is at 51, so just right after the 50 here. This is going to be my box. Okay, and then my other whisker. Now, here's the thing. That 111, that's the outlier, right? So I'm going to put that on here with like a blue. And I'm going to use a little star. So 111 should be about, oh, I don't know, here. That star was like terrible. What did I do? Okay, there's our outlier. And then our next highest number, this is where we needed this, is 83. So we're going to come here. This is 75. There's about 83, probably about here. Come up here, just do a vertical line like that. Your whisker there. Okay, so this is going to be our modified box plot. And then we're going to see now. Oh, I want to show you the outliers. So the outlier, I'm sorry, the fences. So your fences here, -44 and 108. So some people put these on the graph using like little parentheses. I don't personally put them on the graph, but I can show you where they are. I'll put them down here even. 108, see, here's 108. Sorry, well, 100, probably 108 is about there maybe. Anything beyond that is going to be an outlier. That's your upper fence. -44 is like way over here. Maybe not that far. Okay, that might have been a bit of a stretch. Probably about there, actually. Put that there. Okay. But, I mean, regardless, our graph doesn't even go that far, so it doesn't really matter. But those are your fences, right? So if you're talking about your fences, that's how you can look at that. It's any number that's outside of the fence, right? If you're on the outside looking in, you're an outlier. The outside of the fence. So that's how we would do those three things. So now that we've done those three things, now let's describe the distribution of the data set and identify any outliers. Now, good news, we've already identified the outlier. It was 111. So I'm going to go ahead and just say outlier is 111. And what's the shape? Now, I think I already gave away the answer to this, but look at the histogram here, and this definitely has a skewed right look. Okay, if we look at our stem and leaf plot, again, turn it on its side, right? Or turn it where these stems are on the bottom here. And if you kind of draw the shape here, so if I just kind of come up like this, and down, 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 down. That sure looks like a right skewed graph to me. I'm going to do this one over here too. I'm going to not cut through my numbers though. Yeah, that looks terrible. Let me just not do that on that one. I think that one's obvious. Okay, and then on your modified box plot, right? You see that there too. You see you've got the longer whisker here on the right side. So, and then it's a wider box on the right side as well. So yeah, this is overall a right skewed graph. Or you can say skewed right. So I'm going to say, I'll say skewed right. Or right skewed, however you want to say that. It means the same thing. Okay. What measure of center would be most appropriate for the data set? So remember just a second ago we said if it's a skewed data set, we need to use the median. Okay, because of those outliers, those extreme values, the mean is going to be pulled in the direction of those outliers and those extreme values. So for this one, we would use the median since it is a skewed graph. And I'm looking at my spacing here and I'm thinking maybe I have too much space. I don't know. That looks okay. I think it's good. Good for you guys because then you can take more notes on your paper here. Okay, let's see here. Maybe I can do page 4 and then after page 4 end this one and then do the then start a new video for the next set of pages. Okay, so it says use a graphing calculator to calculate each of the following statistics for the data set in problem number 4. Report each with proper symbol and rounding. Okay, so the data set I'm referring to is the one we actually already put in our calculator, so that's kind of handy. We have a lot of these things here, so I'm going to go ahead and pull up the calculator. We're looking for mean. Now remember, this is a sample, right? Sample. So I'm going to make a little note of that here, that we are talking about a sample, right? They took a survey of, what did they say? How did they word that? A random sample of 25 surfers. Yeah. So that means that when we're doing all of our notation, we're using sample notation. So let's just start with notation and then we'll come back and find all the numbers. So for sample mean, we use, you guys should all know this because I like really harped on this at the beginning of the semester. You guys should really know your notation. This is going to be X bar. For mode, there's no notation for that. We just state them. Sample standard deviation, that's going to be an S. I'm going to put this here. X bar equals. Median, that's that capital M. Not that important, but it is there. Range is a capital R. Variance. Okay, so variance is S squared. And we really didn't do a lot with variance. So I don't expect you to really remember that one. Interquartile range, I mean, that is it. That's your notation there, IQR. Lower fence, not really notation there. I just abbreviate it as LF. And then upper fence, I abbreviate it as UF. And then here I just write the word mode equals. Okay, so that's our notation. Okay, when we talk about proper symbol and rounding, the rounding here, so when you do mean, standard deviation, variance, all of those, when we round those, we're going to round them to one more decimal place than what our original data was. Our original data was whole numbers, integers. I guess there are whole numbers also. So they were whole numbers, and in that case, when you do your mean and your standard deviation, you will round them to one decimal place. So it's always one more than your data, your initial data set. So let's go on our calculator. Now remember, I did already type this in here, and we already went to one of our steps. So we have pretty much everything we need here. So you'll see at the very top where you see X bar, remember the calculator is always going to tell you X bar whether or not you put in population data or sample data. The calculator assumes you don't know a population data, that you only know sample data. So the way the calculator was programmed was that they're just going to put X bar there because more often than not, the data you're putting in there is a sample. And so they're assuming. Now, you know, of course, if the data you put in is a whole population, right? So if you put in population data, then the symbol you should be using would be mu. Okay, even though the calculator says X bar, the calculator assumes you put in sample data. Now, we did put in sample data this time, so X bar is correct. I just wanted to make that as a point. Okay, so X bar, 35.64. We're going to round only to one decimal place, so that would be 35.6. So let's go back here. So 35.6. And actually, we should go ahead and put some units on here. I mean, we're talking about surfers, I think. Or no, it was time in seconds, was it? Let's go back. Our data is talking about, internet surfers. Web surfers, not real surfers. And we're talking about the amount of time in seconds that a random sample of 25 web surfers spent viewing a web page. Okay, so this is going to be the amount of time they spent. So the mean amount of time is going to be 35.6 seconds. Okay, so I'm just going to go back over here, and we're gonna go ahead and put that in there. I don't think I put that in my answer key, but that's okay. We'll just put it here to be complete. Seconds. Okay, the mode. So mode comes down to which number appears the most number of times. And if there's more than one that appears the most number of times, then you list them all as modes. So I come through here and I'm looking for anything I see 2 12s, 2 27s, 2 51s. And that's it. Nothing appears more than 2 times. There are 3 numbers that appear 2 times. So 12, 27, and 51. 12, 27, and 51. The standard deviation, let's go back to the calculator screen here. Oh, we can see it right here. Standard deviation, remember, we're looking for S because this is a sample, not a population. So we're not even going to look at sigma. That's for population. Our sample is going to be 27.6. 27.6. And that's also going to be in seconds. Okay. The median. So we found the median, actually in the previous page, the median we found was 27. So 27 seconds. The range. Okay, so range is one of those things that generally, honestly, don't really use all that much. It just doesn't really give us anything that's super valuable. But the range is the biggest number minus the smallest number. So for this one, that would be, so I'm going to go ahead and just put here max minus the min. So that would be, in this case, 111 minus 4. And that's not going to be given to you on the calculator. You just actually have to calculate it, and it's 107. Okay. Seconds. This also would be in seconds. So let's see. Variance. Okay, so here's how we find variance. Okay. You're probably thinking, oh, we just take 27.6 and square it. Or at least I hope that's what you're thinking. And you'd be on the right track if you said that. The thing is, though, if we square this number where it's rounded, our variance is going to not be right. We're going to have to actually write down the entire value of S and then square that value. So luckily, I already have that written down. So S, I'm just going to write up here, is 27.60718506. And when I square that number, okay, I get 762.2. Okay. So this here is what we're going to use for variance. Like I said, if we haven't even worked with variance at all semester. Interquartile range, we found that on the previous page, right? You took your third quartile minus the first quartile, so Q3 minus Q1. I'm just going to go ahead and write down what we found already, 38. The lower fence, again, we have that formula, which is Q1 minus 1.5 times the interquartile range, which we found to be negative 44. And then for the upper fence was Q3 plus 1.5 times the interquartile range, and we get that one to be 108. Okay, I think that completes that little table there. Just as a side note, let me see if I have some, I don't really have a lot of space here. But I guess I'll just mention it, so maybe you can write it down somewhere. If you're dealing with population data, then the symbol for mean is mu, and the symbol for standard deviation is sigma, and the symbol for variance would be sigma squared. So, okay. So number 6 says, how does this keep happening to me? Use the empirical rule to compute percentages. If a bell-shaped distribution has a mean 50 and standard deviation 10, what approximate percentage of data values would be less than 70? Which data values would be considered usual, not unusual, usual in this bell-shaped distribution? Okay, so let's go ahead and we'll draw. Gosh, I'm terrible at drawing these. That's all right. That's not bad. Okay. So right here in the middle, this is the mean, which would be 50. Okay. And then we have with the empirical rule, so I'm going to put up here mean is 50 standard deviation 10. Okay, so in order to use the empirical rule, then we need to go up 1 standard deviation, 2 standard deviations, 3 standard deviations. Okay, every time you go up by 1 standard deviation, you're adding on your standard deviation, right? So if I go from 50 and I go up 1 standard deviation, that's going to put me at 60. And if I go up another standard deviation, so 2 standard deviations, I'm now at 70. 3 standard deviations, I'm at 80, right? Now, if I go backwards, right, I go below 1 standard deviation, 2 standard deviations, 3 standard deviations. Well, 50 minus 10 is going to be 40. And then minus 10, 30. Minus 10, 20, right? This is just a number line, okay? This is a number line. So don't think that you're looking at something that's foreign. I mean, this is really a number line. How do you put numbers on a number line, right? You're saying, okay, the mean's right in the middle. Hence measure of center, right? Now, the empirical rule states that you've got 68% within 1 standard deviation. You have 95% with, okay, hold on. That should have said within. within 2 standard deviations, and 99.7% is within 3 standard deviations. Okay, so 1 standard deviation is from here to here. Okay, this is one standard deviation. This is 68% of your data between 40 and 60. Okay, your 2 standard deviations, that's here and here. So from here over to here, let me draw that a little bit taller. This is going to be 95% of your data. And then your third ones, right? So from here, this is your 3 standard deviations away right here. Okay, this is 99.7%. Okay. So the question says, what approximate percentage of data values would be less than 70? Okay. So let's start there. Less than 70. I'm going to use a pencil here. So less than 70 is going to be this whole shaded region, like from here over. What color should I use? Blue, maybe? Okay. Less than 70. That's like all of this. Okay. That's all of that. So I know that here from 30 to 70, that's 95% of my data, right? So let me just I'm going to like undo my shading so that we can actually see this picture a little bit better. One of the best things about having this tablet, I can do that. Okay, so when we're talking about from 30 to 70, that's 95% of our data, right? Which means what's left in the outside, right? If this is 95%, then your outside pieces have to add up to 5%, right? So this part from here to here, and this part from here, well, I should just draw a little arrow there. Okay. This should add up to a total of 5%, right? So 95%. Well, if this adds up to a total of 5%, that means each one of these is 2.5%, right? This has to be 2.5. This has to be 2.5, right? Altogether 5%. So if I took 5% divided in half is 2.5%. Okay. So I guess I should start with my first step, which was taking, I'm going to put a box here. This is the empirical rule, by the way. right here, what I put up here. Okay, we start by taking 100% minus 95%, which equals 5%. Then we took 5% divided by 2, which gives me 2.5%. That's how I found what's on either side of this. Okay, so what I want to know is the total of everything that's less than 70, right? So again, we shaded, maybe I'll do it a little bit differently. Everything from here, right? That's what I'm looking at, all of that shaded region there. Okay, well, this is 95% plus another 2.5%. That will be 97.5%. Okay, so 95% plus 2.5% equals 97.5%. Okay, so that's how you would find that. That's the first question, right? What approximate values? Okay, which data values would be considered usual in this bell-shaped distribution? Remember that anything that is within 2 standard deviations is considered usual, right? Anything beyond 2 standard deviations is considered unusual. So 2 standard deviations, we said, is from 30 to 70. So which data values would be considered usual? Everything, okay, so usual data is in this interval, 30 to 70. Okay. All right. So, let's see. The next thing we're looking at. Sorry, I just had to breathe for a minute. All right. So, okay, interpret z-scores, percentiles, and quartiles. Okay, if your exam grade is at the 3rd quartile, what does this tell you about your exam relative to the other exam score? Okay, so 3rd quartile, right? This is the top. Well, let's see. All right, the 3rd quartile. So Q3. What does that equal in terms of percentiles? So in the 3rd quartile, that means that that's 3 out of 4, right? In other words, if you wanted to convert that to a percentage, be 75%, 3/4, right? So in other words, the 3rd quartile is the 75th percentile. Okay, so if we're talking about percentiles, remember the definition of a percentile means that 75% of all exams had a score less than or equal to this score, right? That's what that means, right? So what does this tell you about your exam relative to the other exam scores? I would say 75% of other exams were the same as or lower than mine. Okay. Let's see. And then, so that's it. Just the definition of percentile. Well, converting quartile to percentile. So I'm going to put a little side note here. 3/4 is equal to 75 hundredths. Okay, so quartile means fourths. Percentile means hundredths, right? So 4 quarters in a dollar and, 100% be percentile, right? Okay, last one on this video, and then I'll do another video. If your exam grade has a z-score of -1.5, what does this tell you about your exam relative to the other exam scores? Would your exam score be considered unusual? Okay, so if my exam grade has a z-score of -1.5. Well, first of all, I'm sad because it's negative. What that means is I'm below the mean. Okay, if it was positive, it would be above the mean, and that would be great, right? But yes, -1.5 means that I am 1.5 standard deviations below the mean. Okay, so I would say my exam is 1.5 standard deviations below the mean. That below, this is where that negative goes. Notice I put +1.5, but that negative comes into the word below. Okay. Then it says, would your exam score be considered unusual? No, because remember I just said it has to be outside of 2 standard deviations. This is still within 2 standard deviations. Now, if it was negative 2.5, then it would be considered unusual because it's more than 2 standard deviations away in either direction. So no, my exam score would not be considered unusual. My exam grade is not unusual. Okay, so that's it for this video. I'll do another video for starting on page 5.